So this video is on 2D shapes, and the first thing that we're going to look at is symmetry and rotational symmetry. So symmetry is a term that you might have heard of before. So I have an example of symmetry here. And this is the letter A, capital A, is symmetrical, and that dashed line there shows the line of symmetry, and that is the only line of symmetry in this shape. And that is because I could fold it along this line and it would give me exactly the same thing. So that letter A has one line of symmetry. People often talk about, like the idea of beauty and having a symmetrical face and having the gap between your teeth and centre and things like that. Another one we have here is a butterfly. This is symmetrical, and you can see the line of symmetry there. If I fold it, it's exactly the same. Now, symmetry is quite something that we've all come across before, but then we have this idea of rotational symmetry. So, for example, I'm going to take this shape here, and rotational symmetry is when you spin it by an angle, so it could be, so this one, if I spin it by 90 degrees to there, I end up with the same shape, and then I can spin it by another 90, get the same shape, another 90, and I'd end up back where I'd started. So this shape has rotational symmetry order 4. This is the kind of mathematical harder way of saying that there are 4 positions in which it looks the same. So 4 changes in which it looks the same, kind of like, you know, those things that spin in the garden. If we then look at this shape, letter A, this shape here, and we want to find the rotational symmetry, there's no way we can sort of rotate this A to get an A unless you go the full way around. So that is also called order 1 rotational symmetry. So the only way you can create this A by spinning it is if you have it, if you do the 360, if you have it in the position it was originally in. This, however, order 1, is also known as no rotational symmetry, so that's what we say. So anything with rotational symmetry order 1, which means that the only way you can be itself is by being itself or doing a whole loop, that means we say it has no rotational symmetry. So this here, we say has one line of symmetry, but no rotational symmetry. And that's the same with this butterfly. So the one line of symmetry there, the only way you can spin this and get back the butterfly, the only angle is if you go the full way, and that means it has no rotational symmetry. I'm now going to bring in 2 shapes, and these are regular polygons. Okay, so this is a 5-sided regular polygon, and this is a 10-sided regular polygon, also known as a decagon. And the fact it's a regular polygon means that all these lines are the same length and all the interior angles are the same. So if you have a 5-sided regular polygon, also known as a pentagon, that means that there are 5 lines of symmetry and it has order 5 rotation. So if I draw on these 5 lines of symmetry, so we have one there. And the reason I know that is because if I fold it on any one of these lines, so we'll take that one, it folds exactly. If I take another line, let's do this one, again the same thing happens. So if it's a 5-sided regular pentagon, that means it has 5 lines of symmetry. It also means that its rotational symmetry is order 5 because I can put it to there, I have the same shape, that's 1, 2, I have the same shape, 3, I have the same shape, 4, I have the same shape, and then that would be back to where we started. If we now expand that to the 10-sided regular polygon, so a decagon, it has 10 lines of symmetry and rotational symmetry order 10. So I could go there, same shape, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that's back to where we started. And these lines here already marked on are the lines of symmetry because I can fold it and get the same shape back. So I think you can see the pattern that 5-sided means you get 5 lines of symmetry and rotational symmetry order 5. So a 10-sided regular polygon is going to have 10 lines of symmetry and rotational symmetry order 10. So now we're going to move on to types of triangles and quadrilaterals. Okay, so types of triangles. There are 4 types of triangles, so I'm going to split this into 4. The first triangle we're going to look at is this triangle, and this is called the Equilateral Triangle. And that is because all of the angles are equal and the size of all the lengths are equal. So it's quite an easy one to remember: equilateral, equal interior angles, equal lengths. So now if we use our symmetry and order of rotation knowledge, it has 3 equal sides and 3 equal angles of 60 degrees, and it has, if we think about this, it's going to have a line of symmetry here, because I could fold it there and get the same shape. It also has one here, because I could fold that and get the same shape, and it also has one here, because I could fold that and get the shape. So that means it has 3 lines of symmetry and rotational symmetry order 3. And the reason for this is it's actually a regular polygon, but it's 3-sided. So from the bit we just learnt, we know that if it's a 3-sided regular polygon, that means it has 3 lines of symmetry and rotational symmetry order 3. So it's quite a self-explanatory one. Here are your lines of symmetry. And then if we rotate it, you could go to there, same shape, that's 1. There is the same shape, that's 2. And there is the same shape, that's 3. Our next triangle we're going to look at is a right angle triangle. And the reason you can tell it's a right angle triangle is this symbol here, and that shows that the angle is 90 degrees. This is the type of stuff you use SOHCAHTOA and Pythag on. So if we look at this shape and we try and create lines of symmetry, it actually doesn't have any, because there's no line that we could fold this triangle on in which it would kind of look the same and fold neatly. And there's no way we can rotate this around and get the same thing without rotating it fully around. So this has no symmetry and no rotational symmetry. Now we're going to look at this triangle here, and this is called an isosceles triangle. And for this triangle, the key facts are it has 2 angles the same at the base and 2 lengths the same. So it's not quite an equilateral because it doesn't have all 3 the same, but it has 2 angles the same, 2 lengths the same. Okay, now let's try and look for some lines of symmetry and some order of rotation. So is there any line in which I could fold this along and get the same thing? Yes, there is, straight down the middle. I would fold that and it would fold neatly. I couldn't do that, I couldn't do that, so there seems to be only one, and that's down here. So it has 1 line of symmetry. Now let's look at rotational symmetry. So can I rotate this and get the shape back in any way? No, nope. That doesn't seem to have it. No, so the only way I can get that shape is by doing a full circle, so that means it has no rotational symmetry, or order 1. Our last triangle is this, and this is called a scalene triangle. Now this is one in which all 3 lengths are different and all angles are different. And there's no way we can really fold this, which is kind of obvious, no line in which it's going to fold neatly. So that means it has no symmetry. And can we change it in any way to get itself back? No. So no rotational symmetry. Okay, so there are the 4 triangles we need to know. Equilateral, it's quite self-explanatory. Isosceles, 2 angles the same, 2 lengths the same. Right angle, look for that 90 degrees, and then scalene is the only other option of just random. Okay, so quadrilateral, first one, classic one, we all know this one, and that is the square. Now let's look at the angles inside a square. So these are all 90 degrees, so you could do this symbol on all the corners. What about the symmetry? So I could fold it here. Therefore, we just had 4 different lines, which I'll mark on now. So we have shown that it has 4 lines of symmetry. What about rotational symmetry? So how many ways can we rotate this by having exactly the same thing. So we could do it 90 degrees like that, and yeah, it looks the same. So that's 1, 2, same, 3, same, and then that would be back to our start. So rotational symmetry, order 4. Now we move on to the rectangle. So as we know, this is where these two sides are the same length and these two sides are the same length, and then these are all right angles, so kind of an extended square. So let's look at the symmetry. So I can fold it here and get the same shape. No, so we had 2 lines there. And then the rotational symmetry, so how many times can I shift this and get the same thing back? So no, there, that was 1, and then that second one, that brings me back to where I was, so that means order 2, so rotational symmetry, order 2. We now move on to this shape, which looks which is like a diamond that way, or there, but that's not actually a diamond, it's called a rhombus. A rhombus is like a square, but pushed over, so I had a square and I've gone pushed him over. So let's try and see how many lines of symmetry there are and what is the rotational symmetry. So I could fold it along this line. There are 2 lines of symmetry. And what is the rotational symmetry? So how many times can I spin this before I get it the same shape back? So there's 180 degrees, and that gives me the same shape. And then I go another 180 to get 360 back where I was. So that means I've got order 2. Our next shape is this one, and this is the rectangle pushed over. So it was a rectangle, I pushed that one over. And that is also known as a parallelogram because these all parallel. Now let's try and look for some lines of symmetry in the parallelogram. So where can I fold it and it will go neatly? Basically, don't waste your life on this. There are no lines of symmetry in a parallelogram. However, don't get too disheartened because we've still got rotational symmetry to go. So is there a way we can spin this and get the same shape without going all the way around? So there's a 180, and yet we have the same shape, so that's 1. And then if we do another one, it gets back to where we were. So that means, again, like this one, order 2. So next we have this shape, and this has different lengths here, so it's called the trapezium. So it has 1 pair of parallel lines, which are this one and this one are parallel. Is there any way we can fold this to get a nice neat fold? So are there any lines of symmetry? Now it's a bit of a funky shape, and again, there are actually 0 lines of symmetry for this. That doesn't tell us necessarily that it has no rotational symmetry, so we've still got to check this. So is there any way we can spin this, get the same thing back without going all the way around? Nope. The only way to get that itself is to come back to itself. So there's also no rotational symmetry, so trapezium is a bit boring. Now we have our final shape, which is the kite. And now you can see why kites are called kites, because they are the shape of a mathematical kite, which I'm pretty sure came first. So a kite has 2 pairs of equal sides, so these 2 here are the same length, and also these ones up here are the same length. And these angles here are the same. So 1 pair of equal angles. Let's see if we can fold this and get the same shape. There doesn't appear to be another one though, so we've got that one there. What about spinning this kite to check for rotational symmetry? So can we get it back? That's not quite the same. No, no, definitely not the same. No, the only way we can get it back is by going the whole way, so that means it has no rotational symmetry. Okay, so that's all your shapes, and then that's a lot of practice with working out symmetry, lines of symmetry and rotational symmetry. In the exam, you probably can't just go cutting up your exam paper and get a lot of shapes, but you've just got to visualise your head, that thing turning around. So it's a lot of imagination.